Before we can understand the arrival of our new visitor, we must travel back in time to an encounter that left us with more questions than answers and that set the stage for everything that would follow. We must speak of the shadow cast upon our understanding of the cosmos by the first interstellar messenger we knew had visited us. Its name was Oumuamua, a Hawaiian word meaning the scout, or a messenger from afar arriving first. And its arrival in 2017 was so brief, so strange, and so enigmatic that it rewrote our expectations of what might be hiding in the darkness between the stars. Oumuamua was not discovered on its approach, but on its departure. We saw it already from behind, speeding away from us at a dizzying velocity after having rounded the sun. It was a fleeting encounter, a largely missed opportunity that forced astronomers around the world to point every available telescope at this fading point of light in a desperate attempt to decipher its nature before it disappeared forever. And what they found was bewildering. To begin with, its light changed in brightness dramatically and regularly, in a cycle of about 8 hours. This suggested the object had an incredibly strange shape. It was not a sphere, like a typical planet or asteroid. To explain these light variations, models suggested it must be extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or needle, tumbling end over end as it hurtled through space. Other models suggested it could be incredibly flat, like a pancake or a fragment of a ship, spinning like a tossed coin. Whatever its true shape, it was something we had never seen. Its color was also peculiar, a dark red, similar to objects in the farthest reaches of our solar system. A color that suggested a surface rich in complex organic compounds, bombarded by cosmic rays for eons. But the real strangeness, the mystery that ignited a debate that continues to this day, was its movement. As it moved away from the sun, Oumuamua was accelerating. It was moving faster than the sun's gravity alone could explain. In our solar system, we only know of one thing that behaves this way: a comet. When a comet approaches the sun, its ices sublimate, expelling gas and dust in jets that act like tiny rocket engines, giving it an extra push. But when astronomers observed Oumuamua, they saw nothing. There was no coma, the fuzzy atmosphere of gas. There was no dust tail. It was, as far as our most powerful telescopes could tell, an inert, dead rock. So where did that push come from? Several natural explanations were proposed. Perhaps it was releasing a gas invisible to our telescopes. Or perhaps it was an incredibly porous object, a kind of solid hydrogen snowflake, an idea so exotic it seemed like science fiction. And it was in this void of easy explanations that the boldest hypothesis arose. Championed by Harvard astronomer Avi Loeb, he suggested that the only technology we know of that can accelerate in space using sunlight without expelling gas is a solar sail. He proposed that we should consider the possibility that Oumuamua was not a natural object, but an artifact. A piece of extraterrestrial technology, perhaps a probe, a buoy, or simply a piece of debris from a distant civilization. This idea, of course, was met with great skepticism from most of the scientific community, which adheres to the principle that extraordinary causes should not be invoked unless all ordinary explanations have been exhausted. But the mystery remained. Oumuamua faded into the darkness, leaving us with a sense of enigma and a profound feeling of uncertainty. It became the ghost that haunted our theories, and it set a powerful expectation. If this was the first visitor we saw, perhaps interstellar space was filled with these strange, dark, and inexplicable objects. Perhaps the galaxy was a stranger place than we had thought. For nearly 8 years, this was the image we had of the space beyond our home, a place that sent specters, and we waited, longing for the next messenger to give us, if not answers, at least clearer clues. We waited, not knowing that the next visitor, instead of following the ghost script, would tear it up completely, proving that reality, once again, was far more surprising than our expectations. The shadow of Oumuamua was long, and any new visitor would inevitably be judged against it. While the shadow of Oumuamua stretched across the field of astronomy, on Earth, a network of robotic eyes watched the sky relentlessly, night after night. They were not looking for interstellar ghosts or answers to the great mysteries of the universe. Their mission was much more pragmatic and urgent: to protect us. This system is known as ATLAS, an acronym for Asteroid Terrestrial Impact Last Alert System. It is one of our planetary sentinels, a first line of defense designed to detect asteroids and comets on collision courses with Earth, giving us days or weeks of warning, crucial time to prepare or, in the future, to attempt a deflection. Imagine a set of relatively small telescopes spread across the globe from Hawaii to Chile and South Africa. Every night, as soon as the sun sets, their domes open and they begin to methodically scan vast swaths of the sky. They take a picture of a region, wait a few minutes, and then take another of the same spot. The heart of the system is an incredibly sophisticated software that compares these images instantly. It looks for any point of light that is moved against the fixed background of distant stars. The vast majority of these points are known asteroids, members of our solar system that are already cataloged. But sometimes, the software flags something new, an unidentified object that requires the attention of a human astronomer. For years, this system has cataloged thousands of near-Earth objects, performing its silent surveillance. It was a net designed to find known dangers, not to welcome unexpected visitors. And so it was until the night of July 1st, 2025. As the Atlas telescope in Chile conducted its routine sweep, the software flagged one of those anomalies. A point of light, extremely faint, was moving through the constellation of Sagittarius. At first, it could have been mistaken for another distant asteroid, but as the system gathered more observations over the following hours and days, astronomers began to plot its orbit. And that's when the routine was broken. The object's trajectory was not a closed ellipse, the familiar curve of an object bound to our sun's gravity. It was an open hyperbola, a curve indicating that the object came from the vastness of interstellar space, that it was just visiting, and that after its brief encounter with our sun, it would depart, never to return. The news electrified the scientific community. The long silence was over. The second interstellar visitor had been found, and this time we had seen it coming. Unlike Oumuamua, which was detected as it was leaving, 3I Atlas was discovered on its approach, giving us months of preparation time to study it in detail. A global alert was sent to observatories around the world. The message was clear: drop what you are doing and point your telescopes at this point of light. From the deserts of Arizona to the peaks of the Alps, the eyes of humanity turned to the newcomer. Space telescopes, including Hubble and the James Webb, rescheduled their agendas to prioritize this once-in-a-generation target. It was during these first feverish observations that the first and most fundamental of our expectations, the one forged by the strangeness of Oumuamua, was shattered. When the great observatories focused their vision, they did not see a sharp star-like point of light. They saw a diffuse smudge, a small, faint, blurry cloud enveloping a bright core. The object had a coma. It was a comet, an active, living comet, releasing gas and dust under the growing heat of the sun. This revelation, though it might seem anticlimactic after the mystery of Oumuamua, was actually the first clue that this new visitor was not just an object, but a revelation that would change everything. The implication was immediate and profound. Oumuamua, being an inert and strange rock, had made us wonder if our solar system, with its vast swarm of icy comets, was a rarity. But 3I Atlas, by behaving exactly like a long-period comet from our own system, painted a different picture. It suggested that the process that formed our solar system, a process that creates these icy worlds in its outer reaches, might be a common process throughout the galaxy. The existence of a normal comet from another star was a powerful argument that we are not a cosmic anomaly. Suddenly, the universe seemed a little less strange and a little more familiar. The sense of isolation that Oumuamua had hinted at began to dissipate, replaced by a possible sense of kinship with that unknown star system from which our visitor came. The ghost of the first visitor had been replaced by the tangible presence of a pilgrim. But this pilgrim, though familiar in appearance, brought with it secrets of a past so deep and a history so violent that our newfound sense of familiarity was also about to be shattered. With the confirmation that 3I Atlas was a comet, the scientific community entered a more serene and systematic mode of study. The panic of chasing a ghost like Oumuamua was replaced by the thrill of having a cosmic laboratory flying through our own home. For the first time, we could study a comet from another star system up close and compare it to the thousands we have studied from our own. It was an opportunity to establish a baseline, to create a Rosetta Stone that would allow us to translate the features of our comets to those of other star systems. And to do that, astronomers began to dissect the visitor, layer by layer, using the light that reached us across billions of kilometers. The heart of any comet, its essence, is the nucleus. This is the solid central body, often aptly described as a dirty snowball. Imagine a porous, irregularly shaped body, a few kilometers in diameter, composed of a mixture of water ice, frozen gases like carbon dioxide, carbon monoxide, methane, and ammonia, all mixed with dust, rocks, and dark organic compounds. Early observations of 3I Atlas suggested its nucleus was relatively small, perhaps no more than 5 or 6 kilometers in diameter, but remarkably active. This nucleus is, in essence, a fossil. It is a pristine, unaltered sample of the original material that formed its native star system 8 billion years ago. Every grain of dust, every molecule of ice within it, is a letter in a text about the creation of a world that no longer exists. As this icy nucleus hurtles toward the heat of the sun, its ices begin to sublimate, passing directly from a solid to a gaseous state without becoming liquid. This release of gas also expels the dust and rocks it was mixed with, creating a vast, glowing atmosphere around the nucleus. This atmosphere is the coma. Although the nucleus of 3I Atlas was small, its coma grew to an immense size, likely exceeding 100,000 kilometers in diameter, a ghostly cloud much larger than the planet Earth. This glowing halo is what allows us to see comets from so far away. Many of them glow with a greenish hue, a signature of molecules like cyanogen and diatomic carbon, which, when bathed in the sun's ultraviolet radiation, become excited and emit light at that specific wavelength. The coma of 3 Atlas showed this classic behavior, appearing, for all intents and purposes, like that of a familiar comet. But the beauty of a comet is fully manifested in its tails, and 3I/Atlas was no exception. As it approached, it developed not one, but 2 distinct tails, each formed by a different process and telling a different story. The first is the dust tail. It's composed of the heavier particles, the grains of dust and small pebbles released from the nucleus. These particles are too heavy to be significantly affected by the solar wind, but are light enough to be gently pushed by the pressure of sunlight itself. This gentle but constant force pushes the dust away from the sun, creating a broad, diffuse, and often curved tail, which tends to follow the comet's orbital path. It shines with a yellowish-white color because it is simply reflecting sunlight, just as a cloud of chalk dust would in the sky. This second tail is the ion tail or plasma tail. It is much more ethereal and spectacular. It is formed by the gases that sublimate from the nucleus. The sun's intense ultraviolet radiation strips electrons from these gas atoms, ionizing them and giving them an electrical charge. Once charged, these particles are no longer influenced by sunlight, but by the solar wind, that constant stream of charged particles flowing from our star. The solar wind is much more powerful and faster than the pressure of light, so it grabs these ions and drags them in a perfectly straight line, directly away from the sun. This tail glows with its own light, often an electric blue, as the ions recapture electrons. That is why a comet can travel in one direction, but its ion tail always points like a cosmic weather vane, showing the direction of the solar wind. 3I Atlas exhibited this textbook anatomy perfectly. It had an active nucleus, an expanding coma, and two magnificent tails. It ticked all the boxes. For many, the case seemed closed. The visitor was a long-period comet, indistinguishable from those originating in our own Oort cloud. The conclusion seemed obvious. Planetary systems throughout the galaxy form in the same way and produce the same results. It was a comforting conclusion. But in science, comforting conclusions are often the prelude to a much stranger truth. The box was open, and inside, there seemed to be exactly what we expected, a comet in all its glorious and predictable anatomy. But this sense of familiarity was an illusion, the calm before a storm of discoveries so profound that they would make us question not only the nature of this visitor, but the very history of the galaxy. To decipher the secrets of an object as distant and ephemeral as 3I Atlas, a single observation is not enough. It requires a coordinated campaign, a symphony of the most advanced instruments our civilization has created. The story of the comet, from this point on, becomes intertwined with the story of two of the most extraordinary observatories ever launched into space, the Hubble Space Telescope and the revolutionary James Webb Space Telescope. First, the Hubble. For over 3 decades, it has been our persistent eye on the cosmos, an icon of human curiosity floating in Earth's orbit. Its sharp vision in the visible and ultraviolet light spectrum is perfect for capturing a comet's portrait. Hubble was dedicated to studying the morphology of 3I Atlas, the size and shape of its coma, the structure of its dust tail, and how its brightness changed as it rotated and released gas. It was the photographer tasked with capturing the visitor's external beauty, documenting its behavior for posterity. But to read the comet's soul, we needed a different kind of vision. We needed the James Webb. The JWST is an engineering marvel, with its giant golden mirror designed to capture the most subtle form of light, infrared. Infrared light is in essence heat, and herein lies its almost magical power. While Hubble sees the sunlight the comet reflects, Webb can see the light the comet's molecules emit as they are heated. Each type of molecule, water, carbon dioxide, methane, vibrates in a unique way when it absorbs heat, and in doing so emits an unmistakable infrared light signature, a thermal fingerprint. The James Webb is not just a photographer, it is a chemical detective capable of identifying every ingredient in this ancient traveler's recipe. The technique that both telescopes, along with large ground-based observatories, use to read this information is called spectroscopy. It is perhaps the most powerful tool in astronomy, and it works on a principle of astonishing elegance. Imagine sunlight as pure white light containing all the colors of the rainbow. When this light travels through the gas in the comet's coma, the molecules in that gas act like tiny filters. A water molecule, for example, will absorb a very specific set of colors or frequencies of light, while a carbon dioxide molecule will absorb a completely different set. When that light finally reaches the James Webb's mirror, it is no longer a perfect rainbow. It has dark lines, gaps, where the colors have been absorbed by the comet's molecules. This rainbow with missing lines is known as an absorption spectrum, and those dark lines form a perfect barcode. Every molecule in the universe has a unique and immutable barcode. By reading this barcode, scientists can tell without any doubt which elements and compounds are present in the comet's atmosphere, even if it is hundreds of millions of kilometers away. It is a form of cosmic archaeology, a way to analyze the composition of an ancient artifact without ever touching it. This effort was not limited to space. It was a global collaboration. While Hubble and Webb had the clearest view, large ground-based observatories in the deserts of Chile and on the volcanic peaks of Hawaii also pointed their mirrors at the visitor. Each observatory contributed a piece of the puzzle. Some specialized in measuring the comet's speed with incredible precision, others in analyzing the polarization of its light to understand the shape of its dust grains. It was a testament to the collaborative nature of modern science. Hundreds of scientists from dozens of countries sharing data and working together, united by the common goal of understanding this single, fleeting visitor. Thus, the stage was set. The most powerful eyes of humanity were fixed on the pilgrim. The method for deciphering its message, the language of the light's barcode, was ready. The scientific community, having established that it was a normal-looking comet, was preparing to read a text they expected to be familiar. They did not know that the message they were about to decipher, written in those subtle dark lines of an infrared spectrum, would not speak of a cosmic neighbor, but of a ghost from an immemorial time, a revelation that would shatter the comforting illusion of familiarity forever. While the spectrographs of the James Webb and Hubble were busy analyzing the comet's chemical composition, another team of astronomers was working on a different but equally crucial puzzle. They were the cosmic detectives, the cartographers of the invisible, and their only clue was the visitor's movement. Their task was to take the incredibly precise measurements of 3I Atlas's position and speed and trace its trajectory backward in time in an attempt to find its place of origin. It is a work of immense complexity, like trying to reconstruct the path of a pollen grain in a hurricane, but on a galactic scale. The gravity of our sun, that of the planets, and even the subtle gravitational pull of the Milky Way as a whole are taken into account. The first clue that something was profoundly strange came from this investigation. By projecting its orbit into the past, astronomers noticed that it did not align with the plane of the galaxy in which our sun resides. Most stars in our neighborhood, including our own, belong to what is known as the thin disk of the Milky Way, a relatively flat, dense region full of middle-aged stars like the Sun. But the trajectory of 3I Atlas suggested it was not a member of this club. Its orbit was more inclined, more erratic, characteristic of objects belonging to the thick disk, an older and more scattered population of stars that forms a kind of halo above and below the thin disk. These stars are relics of an earlier era in our galaxy's formation. This was the first red flag. It was as if a visitor arrived in your city and, from their way of speaking and their customs, you realize they were not from a neighboring city, but from a lost and ancient civilization. The team tried to match its trajectory to a known star in the thick disk, but had no luck. There was no clear candidate for its parent star. This meant its journey had not been short, but immensely long. long enough for its star of origin to have moved to a completely different part of the galaxy. It was the combination of these factors, its belonging to the thick disk and the lack of a nearby origin, that led scientists to a conclusion that shook the foundations of planetary astronomy. Using models of how stars move and age in the galaxy, they calculated the most probable age of our visitor. The number that emerged from these complex simulations was simply mind-boggling: 8 billion years. Let's pause to process that number. Our planet Earth is 4.5 billion years old. Our sun is just slightly older. This comet, this pilgrim that seemed so familiar in its appearance, was born almost twice as long ago as our own world. It was formed from the gas and dust surrounding a previous generation star, a star that likely lived and died, becoming a white dwarf or a neutron star, billions of years ago. When 3I Atlas began its interstellar journey, the material that would eventually become the Earth, the oceans, life, and ourselves, was still a cold, formless cloud of interstellar gas, adrift in another arm of the galaxy. This discovery changed everything. Again, the comet ceased to be a simple object and became a ghost that brought with it the echo of a younger, different universe. It became a time capsule, not from another place, but from another era. Its scientific value skyrocketed. Studying its composition was no longer just comparing one solar system to another. It was comparing the chemistry of our galactic era with that of a past one. The galaxy is not static. It evolves chemically. Each generation of stars fuses light elements into heavier ones, and when they die, they scatter these new elements throughout the cosmos, enriching the gas that will form the next generation of stars. We are the product of a chemically rich galaxy. The iron in our blood, the calcium in our bones, were forged in the hearts of stars that died before the sun was born. But 3 Atlas comes from a time when the galaxy was much less rich in these metals. Therefore, its ice and dust represent a direct physical sample of the basic components of planets from that remote era. It is an opportunity to answer fundamental questions. Were the basic components for life as common 8 billion years ago as they are today? How has the recipe for forming planets changed throughout cosmic history? The visitor that had arrived at our door was not a neighbor. It was an ancestor so ancient that it challenged our very conception of time. The question was no longer whether other solar systems were like ours. The question now was what our universe was like so long ago that Earth's memory had not even begun. And this ghost, this ancestral pilgrim, still held more secrets in its swift and silent flight. Secrets that spoke not only of its incredible age, but of the violent history that allowed it to survive to tell us its tale. An object so ancient, a pilgrim that has wandered the galaxy for more than half the age of the universe, should logically be a weary traveler. We should expect its movement to be majestic but slow, the worn-out pace of a cosmic elder. But 3I Atlas was nothing like that. It shattered this expectation with an energy that perplexed astronomers. The visitor was not slow. It was the fastest interstellar object we had ever recorded. It was traversing our solar system at an astonishing speed of approximately 209,000 kilometers per hour, or 58 kilometers per second. This is a speed that escapes human intuition. It is fast enough to circle the entire Earth in less than 12 minutes. It is a speed that would allow it to travel from the Earth to the Moon in just over an hour and a half. It is more than 3 times the speed of the Voyager 1 probe. The fastest object humanity has ever launched into space. This was not the speed of a languid traveler. It was that of an interstellar cannonball. And this fact was not a mere curiosity. It was the key to understanding the greatest mystery of all. its incredible longevity. Its speed was its armor, its shield, the reason it had survived for so long. Let's think about the dangers of an 8 billion year journey. The Milky Way is not a benign vacuum. It is filled with gravitational traps. There are over 100 billion stars, each with its own gravity well. A slow comet passing too close to one of these stars would inevitably be captured. It would become an orbital prisoner, ending its interstellar journey. Or it could be sent into a death spiral towards the star itself, to be consumed. Or, if it passed close to a giant planet, tidal forces could tear it apart, turning it into a swarm of debris. Long-term survival for a slow wanderer is statistically impossible. 3I Atlas, however, was immune to this fate precisely because of its speed. It was so fast that it didn't fall into gravity traps. It blasted through them. Its enormous kinetic energy allowed it to slice through the gravitational wells of stars, deviating slightly, but never enough to be caught. Like a speedboat cutting through waves instead of being tossed by them, its speed was the guarantee of its freedom. But this only deepened the mystery. Where had it gotten such speed? It couldn't have been born with it. It had to acquire it. This question takes us back to its violent birth. A comet is not gently pushed out of its star system. It is ejected. The most likely scenario is that of a young and chaotic star system, a true cosmic billiard table. Imagine giant planets, like Jupiter, forming and migrating, altering the orbits of all the smaller bodies around them. In the midst of this chaos, our comet, which until then had been in a stable orbit, was likely diverted towards one of these giants. As it passed by, the immense gravity of the planet acted as a slingshot, a cosmic catapult that launched it out of its native system at a tremendous escape velocity. That was only the first impulse. Over the next 8 billion years, its journey was a long series of accelerations. Its trajectory, which seemed to come from the direction of the dense galactic center, suggests it spent much of its life navigating the most crowded and chaotic regions of the Milky Way. Every time it passed near a massive star or a star cluster, it received another small gravitational push, an assist that increased its speed. Its journey was not a peaceful drift, but a cosmic obstacle course, and at each obstacle, instead of slowing down, it gained more momentum. Thus, our image of the visitor transformed once again. It was no longer just a familiar comet, no longer just an ancestral ghost. Now it was a hardened survivor, a veteran of countless gravitational battles. Its calm appearance, that of a snowball gently releasing its gas, concealed a history of unimaginable violence. The speed was not just a number, it was the autobiography of its journey, written in the language of kinetic energy. Every kilometer per second was a chapter that spoke of a dodged star, a traversed star cluster, a life lived on the edge of chaos. The ancestral pilgrim was not a monk on a peaceful journey, but a projectile forged in violence and hardened by time. And its icy body, its chemical DNA, was the diary that recorded every galactic province it had visited on its epic flight. After an 8 billion year journey through countless star systems, what material did our ancient visitor bring with it? What is this relic made of? To answer this, the James Webb Space Telescope became our primary translator. Its ability to see the universe in infrared light allowed it to analyze the chemical composition of the comet's coma, that halo of gas shed from its icy nucleus. Each molecule, when heated by the sun, emits a unique heat signature, an infrared barcode. And Webb was there to read every line of that code. The first results were, once again, comforting and familiar. The telescope confirmed the abundant presence of the most essential molecule for life as we know it: water, H2O. To see the unmistakable signature of water in such an incredibly ancient object was a profound moment. It suggested that water is not a recent invention of the cosmos, but a fundamental ingredient that has been present in the galaxy for most of its history. The water that flows in our rivers and fills our oceans has an echo in this pilgrim from an era before Earth. Alongside water, Webb detected other old acquaintances from our solar system, such as carbon dioxide, CO2, and carbon monoxide, CO, gases that are found frozen in our own comets. But the real science, the kind that changes everything, is often found in the details, in the subtle deviations from the norm. And here, 3I Atlas did not disappoint. While the ingredients of its recipe were familiar, the proportions were strange. Imagine finding a recipe for bread from an ancient civilization. You recognize the flour, water, and salt, but the recipe calls for 10 times more salt than water. You know immediately that although they used the same ingredients, their world, their kitchen, was fundamentally different. This is precisely what scientists began to see in the data from 3I Atlas. Webb's analyses revealed that the comet was unusually rich in carbon monoxide and carbon dioxide compared to the amount of water ice it possessed. This ratio is a kind of cosmic thermometer that tells us about the comet's birthplace. In a forming solar system, different ices condense at different distances from the central star. Water ice can form relatively close, but supervolatile ices, like carbon monoxide, can only freeze and become part of a comet in the coldest, most distant regions of a system, very far from its star. The abundance of these volatile ices in 3I Atlas gave us a direct clue about the architecture of its native star system 8 billion years ago. It suggested that it probably formed in an extremely cold region, far beyond its star's snow line, in a carbon-rich environment. For the first time, we were not theorizing about what other planetary systems might be like. We were analyzing a physical sample of one, and an incredibly ancient one at that. We were reading the history of the temperature and composition of a planetary nursery that no longer exists. And amidst this strange recipe, the search focused on the most sought-after ingredients, complex organic molecules. These carbon-based molecules are the bricks with which life is built. The theory of panspermia postulates that these bricks did not necessarily originate on Earth, but could have been brought here by comets and asteroids that impacted our young planet. Finding these molecules in an 8 billion-year-old relic would be one of the strongest pieces of evidence for this idea. It would mean that the basic components for life are ancient, common, and travel between the stars. As the James Webb continued its analysis, the data began to show the signatures of methane, ammonia, and potentially more complex compounds. The ancient pilgrim was not only a messenger of time and violence, but it also seemed to be a bearer of the ingredients of life. It did not bring life itself, but the promise, the potential. Its message, written in a language of chemistry, seemed to tell us that the universe has been seeding the cosmic fields with the precursors to biology for almost its entire history. Each molecule was a word, and the proportion of those molecules was the grammar of a forgotten language. The James Webb was not observing a comet. It was reading the recipe of a lost world, a recipe that showed us that although the universe uses the same ingredients everywhere, the variety of worlds it can create is infinite. And most intriguingly of all, it seems that in that ancestral recipe, the first ingredients of life itself were written, waiting for a warm, watery place to flourish. As we move deeper into this month of August 2025, the saga of 3I Atlas enters its most dynamic phase. Having established its identity as an ancient and swift survivor with a unique chemical composition, we now follow it on its path. a journey that takes it from the cold darkness of the outer reaches of our solar system towards an intimate and violent encounter with our star. This is not a quiet journey. It is a controlled fall that has lasted for months, and now it is about to reach its climax. After its discovery, beyond the orbit of Jupiter, the comet crossed the first major threshold of our inner solar system. It passed through the domain of the king of planets, Jupiter, whose immense gravity warps the fabric of space around it. A slower object might have been significantly deflected, its trajectory altered by the pull of the gas giant. But 3I Atlas, with its incredible speed, sliced through Jupiter's sphere of influence like a bullet, feeling its pull, yes, but too fast to be dominated by it. Its steady passage was another demonstration of the energy it carried. Next, it entered the asteroid belt, that vast region between Mars and Jupiter, filled with the remnants of a planet that never formed. Unlike the popular image of a dense and dangerous field of rocks, the belt is an immensely empty place. Still, it is a ghostly territory, a reminder of the chaotic processes that shaped our own home. For our visitor, coming from a completely different solar system, it was its first crossing through the debris from the formation of a rocky world like ours. Upon crossing the orbit of Mars, the comet officially entered the inner solar system. This is the realm of the terrestrial planets, a radically different environment from the cold vacuum it comes from. The temperature of space, though still frigid, began to rise significantly. The intensity of sunlight and the solar wind grew exponentially, and the comet, this being of ancient ice, began to react to this new heat in a spectacular way. Its transformation, which had been subtle and slow in the outer reaches of the solar system, accelerated dramatically. What was a diffuse point to telescopes now began to blossom. Its coma, the atmosphere of gas and dust, expanded at an astonishing rate, fueled by the increasingly violent sublimation of the ices in its nucleus. It's like a cosmic flower opening in fast motion, releasing gases that had not seen the light in 8 billion years. For astronomers on Earth, this expansion was a data bonanza, offering more material for the James Webb spectrographs to read and analyze. Its tails also began to grow, unfurling like celestial banners. The wide, curved dust tail, reflecting the sunlight, became brighter and more prominent, and the thin, straight ion tail, glowing with its own ethereal blue light, stretched for millions of kilometers, a cosmic finger pointing directly away from the growing tyranny of the sun. The comet, which had been a ghost, was becoming a spectacle. As it moved towards its climax, it grew ever brighter in our sky. Amateur astronomers around the world began to track it, capturing its evolving image and beauty. But this growing magnificence is the external sign of an incredibly violent process. For the comet, this journey towards the sun is a trial by fire. Every particle of gas and dust that is released to create its beautiful appearance is a part of itself that is lost forever. The nucleus, bombarded by the heat, could be cracking and weakening under the strain. This transformation is the preparation for the final act of its visit, the perihelion, its point of closest approach to the sun, which will take place in October 2025. That will be the moment of truth. It will be when the comet is subjected to the maximum thermal and gravitational stress. It will be when it shines brightest, revealing the secrets of its deepest, most primordial layers. And it will be when it runs the greatest risk of disintegrating, of breaking apart under the pressure. The pilgrim has traveled for 8 billion years for this appointment with our sun. For months, we have watched it transform from a ghost into a celestial spectacle. Now, in the final weeks of its approach, it prepares for its brightest and at the same time most dangerous moment. The climax of the visit is about to begin. The climax of 3I Atlas's visit is not a discovery, but an event, a moment of extreme violence and beauty known as the perihelion. the point in its orbit closest to the Sun. For 8 billion years, this comet has wandered the frigid darkness, a realm of silence and temperatures near absolute zero. Now, it plunges into the heart of our solar system to face an inferno of heat and gravity for which nothing in its incredibly long existence could have prepared it. It is its trial by fire, the moment that will determine its fate and reveal its deepest secrets. Imagine the comet's nucleus, that mountain of ice and rock a few kilometers in diameter, now exposed to the direct fury of a star at point-blank range. The surface of the comet heats to hundreds of degrees. Tons of ancestral ice, not just water, but also carbon dioxide, carbon monoxide, and other gases, vaporize every second. This massive sublimation is not a gentle process. It is a series of eruptions and geysers that erupt from its surface, releasing tremendous energy. The comet, in essence, is actively disintegrating, sacrificing parts of itself to create the spectacle of its coma and tails. This moment of maximum danger is also one of maximum scientific opportunity. The Sun's violent heat is stripping away the outer layers of the comet, those that have been exposed to cosmic radiation for eons. For the first time, we are seeing pristine material that has been locked in the heart of the nucleus since its formation. It is the oldest, most unaltered material we have ever had access to. The spectrographs of the James Webb and ground-based observatories work tirelessly during this period, capturing the chemical fingerprint of this newly released gas. They are searching for complex organic molecules and isotope ratios that can tell us the definitive story of the comet's origin and, perhaps, the origin of the ingredients for life in the galaxy. But as scientists collect this precious data, one question dominates the tense wait. Will it survive? History is full of comets that promised a great show and did not survive their perihelion. In 2013, Comet ISON, expected to be the comet of the century, simply vanished as it rounded the Sun, disintegrating into a cloud of dust. The fate of 3I Atlas hangs in the balance. The violent gas eruptions can fracture the nucleus from within, and the immense tidal forces of the Sun's gravity pull on it, threatening to split it into 2 or more pieces. Astronomers around the world watch in real time for any sign of its impending demise. A sudden, dramatic increase in its brightness could be the signal that a major fracture has exposed a huge amount of fresh ice to the Sun. A change in the shape of its inner coma, seen through the most powerful telescopes, could reveal that the nucleus is no longer a single object, but a swarm of fragments flying in formation. Every new image is a medical report on the traveler's health. But 3I Atlas, true to its character as a survivor, defies the odds. It passes the point of maximum danger. It endures the most intense heat and the strongest gravitational pull. Observations confirm that, although it has lost a significant amount of mass and has been rejuvenated by the Sun, its main nucleus has remained intact. Once again, the visitor is not what we expected. Its ability to hold together under such extreme stress is another clue to its nature. It is not a loose agglomeration of ice and dust like many of our comets. It is a robust, dense object, perhaps forged in a more turbulent environment or hardened by its long journey. Its survival is the final data point from its trial by fire. The ancestral pilgrim had entered the dragon's lair, felt its fiery breath, and emerged on the other side, burned and diminished, but whole. Its trial by fire was over. Now, on its way out, the real task began for us, to analyze the scars and secrets revealed in its moment of maximum danger, to build the final portrait of this visitor that, until the last moment, continued to defy our expectations. The climax of its visit has passed, and with it, the long goodbye begins. Having reached perihelion, 3I/Atlas initiated the second half of its journey through our solar system, the way out. Its trajectory, a perfect hyperbola, ensured it. There was nothing that could stop it. Every second it moved further from the sun and from us, its speed still immense, but its destiny sealed. It was on a one-way trip. The climax of its visit was over, and now the long epilogue began, a slow, majestic fading into the night. This return journey was a mirror image of its arrival. It crossed the orbit of Mars again, then the asteroid belt, and finally, the domain of Jupiter. But the comet that left was not the same one that had arrived. On its arrival, it was a mystery, a frozen ghost slowly awakening. On its departure, it was a fire-tested veteran, an open book from which we had read the first and most surprising chapters. It was physically diminished, having lost millions of tons of its ancestral mass in the form of gas and dust, sacrificed to create the spectacle that had captivated us. But it had enriched us with invaluable knowledge. As it ventured back into the cold of the outer solar system, the process that had made it so spectacular began to reverse. The sun's energy diminished with the square of the distance, and the effect on the comet was dramatic. The violet sublimation of its ices slowed to a gentle murmur, and finally, to almost total silence. Its magnificent coma, which had rivaled the size of planets, began to shrink and dissipate, like morning fog as the sun rises. Its bright nucleus, the false star it had created, dimmed. Its two tails, the banners of its visit, also retreated. The wide dust tail, no longer feeling the same pressure from sunlight to push it, slowly dispersed into space, leaving an almost invisible trail of its passage. And the ethereal ion tail, deprived of the same amount of gas and the force of the solar wind, shortened and vanished, its electric blue glow extinguishing. The comet was shedding its finery. It was returning to its primordial state, a dark, silent mountain of ice and rock, resuming its long slumber. It was like watching a flower bloom vibrantly in a single day, only to close and wither as night fell. But for astronomers, this slow fading was not an end, but a continuation of observation. Studying the way a comet powers down is as important as studying how it powers up. The rate at which its activity decreased provided them with crucial data about its composition. The most volatile ices, like carbon monoxide, stopped sublimating first, while the more resilient water ice continued to release gas at greater distances. By monitoring this sequential shutdown, scientists could refine their models of how the different ices were stratified within the comet's nucleus, gaining more clues about the conditions of its birth 8 billion years ago. They also watched carefully for any signs of post-perihelion stress. Sometimes, a comet survives the heat and gravity of its closest approach, only to fracture later, when thermal stress causes deep cracks in its structure. The continued integrity of 3I Atlas as it moved away was the final confirmation of its incredible robustness. It had not only survived its trial by fire, but it had emerged from it structurally sound, a testament to its nature as a hardened survivor. As the months pass and we enter 2026, 3I Atlas will become increasingly faint. Soon, it will disappear from the view of amateur telescopes. Then, only the large professional observatories will be able to follow its trail. And finally, a day will come when even the James Webb Space Telescope will have to strain to capture its last, faint photons. It will once again become what it was when we found it, an anonymous point of light. And then it will disappear. Its brief, brilliant intersection with our history will be over. The comet was dissolving back into the night. Its spectacular bloom, powered by our sun, was temporary. Now it was returning to its natural state, a frozen and lonely pilgrim. It had given us a show and an unforgettable lesson, and as it faded, it left us with the task of putting all the pieces together, of building the final portrait of its message. The physical goodbye was just the beginning of the intellectual hello. The echo of the pilgrim is fading, but its message now resides here, in our computers and in the minds of scientists around the world. Over the coming years and decades, every photon, every spectral signature, every measurement of its trajectory will be analyzed. The visit of 3I Atlas, though brief, has generated an amount of data on an interstellar object that dwarfs everything we knew before. And as we put all these pieces together, the final portrait of this visitor emerges. A portrait defined not by what it was, but by everything we didn't expect it to be. First, we expected a ghost, and we found a living thing. In the shadow of the enigmatic and rocky Oumuamua, we prepared for another strange, inert object. Instead, 3I Atlas presented itself as a familiar, active comet, releasing gas and dust like any comet from our own solar system. This first surprise was a profound relief and a revelation. It told us that our corner of the galaxy is not necessarily an anomaly. The processes that formed our sun and its planets, creating a vast reservoir of icy worlds, are likely not unique. Throughout the Milky Way, countless other stars may be surrounded by similar families of comets, suggesting that planetary systems like ours could be the norm, not the exception. Second, we expected a neighbor, and we found an ancestor. Once we accepted it was a normal comet, we assumed it would come from a nearby star. Instead, we discovered it was a ghost from a forgotten time, an 8 billion-year-old object, nearly twice the age of Earth. This revelation changed everything. It provided us with a physical sample of the Milky Way in a remote era. It showed us that the basic components of planets, the same ices and rocks that formed us, already existed in the galaxy long before our sun began to shine. The comet became a time machine, offering us a window into the chemistry of a younger universe. Third, we expected a weary traveler, and we found a swift warrior. An object so incredibly ancient should have been slowed or captured eons ago. Instead, it arrived as the fastest interstellar object ever seen. Its speed was not just a number, but the scar of a violent history. It told a story of a chaotic ejection from its home system, and a journey of billions of years through the most dangerous regions of the galaxy, using the gravity of stars as slingshots to accelerate. It taught us that the galaxy is a much more dynamic place than we imagine. A place where objects are not just moving, but are launched across the cosmos like projectiles. Fourth, we expected a familiar recipe, and we found an alien formula. When analyzing its composition, we found the ingredients we expected: water, carbon dioxide, carbon monoxide. But the proportions were strange, different from those of our comets. This unique chemical recipe was a fingerprint of its birthplace, a thermometer that informed us about the conditions of a planetary system we will never see. It showed us that, although the universe uses the same elements everywhere, the way it combines them to build worlds is incredibly diverse. Finally, we expected a fragile object, and we found a robust survivor. Its ability to withstand the fiery embrace of our sun, to pass through Perihelion without disintegrating, was the final proof of its extraordinary nature. It was a hardened veteran, a denser and more resilient object than we had a right to expect. This is the final portrait of 3I Atlas. It is not a simple snapshot, but a tapestry woven with threads of time, speed, chemistry, and survival. Each thread has unraveled one of our expectations, replacing it with a deeper, more nuanced truth. 3I Atlas was not just a comet. It was a lesson in humility, reminding us that our theories must always be ready to be rewritten by evidence. a lesson in connection, showing us that our galaxy is an interconnected ecosystem where materials travel between stars, and a lesson about our true place in the history of the cosmos. The comet's message, ultimately, was about time itself. It showed us that we are the newcomers to a universe that has been building worlds and sowing the ingredients of life for an almost inconceivable time. Now, all that was left was to contemplate the final destination of this messenger, its journey back to eternity. The story of our brief intersection with 3I Atlas comes to its end. The messenger, having delivered its text of ice and dust, retreats into the immensity from which it came. We follow it with our telescopes until it becomes a whisper of light, and then nothing, absorbed back into the galactic night. For us, its story is over. But for it, this is simply the end of a chapter, the closing of a brief, brilliant stop on a journey that has no end. Now it faces its natural destiny again, solitude and time. Propelled by the inertia of its encounter with our sun, it will continue its journey through the Milky Way, essentially forever. Its 8 billion-year journey was just the beginning. Now the next one begins. In about 40,000 or 50,000 years, it will graze past another star, perhaps a red dwarf in some constellation we do not even recognize today. It will not be captured. Its speed is too great. It will be an encounter as fleeting as ours. Another brief moment of interaction in an eon of solitude. And then it will go on. It will complete an orbit around the center of the Milky Way every 200 or 300 million years, a great galactic year, along with the billions of stars that make up our galaxy. It will be a ghost ship on an eternal ocean, a silent witness to the birth of new stars and the death of old ones. It will carry within its icy core the chemical memory of a world that died billions of years ago, and it will also carry the scar of its brief, fiery encounter with our sun. It will become an artifact of two eras, a link between two chapters of cosmic history. Its goodbye is final. It will never return. The orbital alignment that brought it to our solar system was an event of astronomically low probability, a cosmic stroke of luck. We have had the privilege of being here. At this precise moment in Earth's history, with the right technology to witness its passage and decipher its message, future civilizations, if they exist, will only be able to read about it in our archives. The feeling it leaves us with is a mixture of melancholy and profound gratitude. Melancholy for the departure of such an extraordinary being, and gratitude for the opportunity to have learned from it. And what is its final legacy? What does this visitor leave us beyond the data and scientific discoveries? It leaves us, above all, with a lesson in perspective. It has given us a perspective of connection. It showed us that, despite the immense distances, the galaxy is an interconnected place. The material from one star system can and does travel to visit another. We are not an isolated island. We are part of a vast galactic ecosystem that has been exchanging materials, the very building blocks of planets and life, for billions of years. It has given us a perspective of time. By bringing us a sample of an 8 billion-year-old universe, 3I Atlas has given us a tangible link to a past so deep it dwarfs our own history. It forces us to see our existence not as the center of time, but as an instant, a blink of an eye in the life of an incredibly ancient galaxy. It reminds us that the universe has been creating and destroying worlds since long before ours was born. And finally, it has given us a perspective of wonder. It has reminded us that the universe, no matter how much we think we know, always holds surprises. There are always new mysteries to discover, new expectations to shatter. It teaches us that we should approach the cosmos not with the arrogance of one who has all the answers, but with the humility and curiosity of an eternal student. The eternal pilgrim continues its journey. Its story is now intertwined with ours, and as you prepare for your own journey into the silence of the night, into the world of dreams, you can carry this comforting thought with you. The universe is not an empty, disconnected place. It is a network of stories, an ocean of time, filled with messengers traveling in the darkness. And our brief existence is our one chance to listen to their tales. The journey continues, always calmly, always at the pace of the universe.